Light bent backwards on a day that defied the laws of physics. This is not a story from fiction, but one of the most baffling events ever recorded in the cosmos. We are going to investigate the day light bent backwards, and the strangest phenomena ever witnessed in space. By the end, you will understand the most compelling theories behind these cosmic mysteries that have left top scientists without answers. What cosmic architecture could cause gravity to seemingly reverse its pull? And why would a deep space void send back a perfect echo of our own past broadcasts? How comfortable are you with a universe that can rewrite its own rules for centuries? The cosmos behaved as a perfect, predictable clockwork. The scientific community of the 1950s and 60s operated with a profound confidence, having built its understanding of reality on the unshakable pillars of Einstein's theory of relativity. This framework elegantly governed everything from the orbit of a planet to the bending of starlight, all hinging on one fundamental constant: the speed of light in a vacuum. Telescopes, growing ever more powerful, scanned the heavens and found only confirmation. Galaxies spun according to predicted gravitational laws, and the universe expanded in a manner that aligned beautifully with mathematical models. It was an era of burgeoning mastery, where any unexpected data point was almost reflexively attributed to instrumental error or some fleeting atmospheric quirk. The scientific method, as celebrated voices like Carl Sagan explained, was a slow, steady, and self-correcting march toward truth. This was the established normalcy, a universe that played by a known and reliable set of rules. That very confidence is what made the first anomaly so utterly destabilizing. A single crack in a foundation everyone believed was made of solid granite. The control room was a temple of quiet concentration, filled with the low hum of machinery and the soft glow of monitor screens. It was 1972, and a team of astronomers was meticulously mapping the sky with a powerful new radio telescope array. Their focus was a brilliant, distant quasar, its light traveling for billions of years to reach them. Their task was routine: to observe how its signal was distorted by the immense gravity of a galaxy cluster lying directly in its path. This phenomenon, gravitational lensing, was a well-understood pillar of Einstein's universe. Massive objects warp the fabric of space-time, acting like a cosmic magnifying glass that bends light around them. The scientists expected to see the quasar's image stretched or perhaps split into multiple copies. What appeared on the data plots, however, was impossible. The light was not bending toward the massive cluster. It was bending away. The sharp lines on the graph veered off in the wrong direction, as if the fabric of space itself were pushing the light back. One researcher reportedly checked and rechecked the calibration of his instruments, certain a wire had come loose or a sensor had failed, but the data was clean. The signal was clear. The laws of physics, as they were written, had just been violated in plain sight. Renowned astrophysicist Dr. Arvind Schmidt later described the moment, stating it was as if gravity had a negative component we never anticipated. His words captured the sheer disbelief of the entire team. Imagine dropping a rock and watching it fall upwards into the sky. That was the scale of this conceptual inversion. The immediate and most comfortable explanation was a profound instrumental error. Perhaps the data processing software contained a hidden bug that inverted the results. Maybe atmospheric interference had created a phantom signal. Yet after months of painstaking review, no error could be found. This forced the scientific community to confront far more radical ideas. The most startling theoretical proposal involved the existence of something called negative mass. We are all familiar with positive mass, the kind that makes up planets, stars, and ourselves. It attracts other mass through gravity. Negative mass, however, would theoretically exhibit repulsive gravity. It would push other matter away. If even a small concentration of this exotic substance existed within that galaxy cluster, It could, in theory, explain why the quasar's light was seemingly repelled. This single anomalous reading from 1972 did more than just puzzle a few astronomers. It forced a foundational re-examination of the most fundamental forces governing our cosmos, setting a chilling precedent for the even stranger temporal disturbances that would soon echo back from the void. Years later, a different kind of anomaly would emerge from one of the emptiest places in the known universe. The Boötes void is a staggering cosmic desert, a region of space hundreds of millions of light-years across that is almost entirely devoid of galaxies. It is a profound nothingness, a place where you would expect to hear only the faint hiss of the cosmic microwave background. So when a deep space monitoring station trained its antennas on this void, the last thing scientists expected was a familiar voice. The signal was a complex radio transmission, clear and structured. After decoding, the analysis revealed something that made no sense. It was a perfect, time-delayed replica of a human-made broadcast from exactly 50 years prior. This was not a simple reflection or a random burst of cosmic static. It was an echo, a perfect copy of a television broadcast that had left Earth a half-century before, now returning from a direction that held nothing to send it back. The implications were immediately staggering. How could a signal travel into a void and return as a perfect recording of itself decades later? It was a direct violation of causality, the principle that cause must always come before effect. The signal had, in a way, met its own past. Experts with the search for extraterrestrial intelligence were completely baffled. Dr. Elena Petrova, a leading figure in the field, publicly stated that this implies either a technology for manipulating space-time we cannot fathom, or a natural phenomenon that copies information. The first possibility, that of an intelligence, was both thrilling and terrifying, suggesting a capability to fold time and space for purposes beyond our understanding. The second possibility, a natural cause, was perhaps even more bizarre. Theoretical physicists began exploring truly exotic concepts. One proposal involved cosmic strings, hypothetical cracks in the fabric of the universe left over from the Big Bang. If a loop of this cosmic string existed in the void, its immense gravitational fields could theoretically act as a lens, not just bending light, but trapping it on a colossal detour through space-time before sending it back toward us. Another idea ventured into the quantum realm, suggesting a macroscopic quantum echo where the information of the signal was somehow imprinted on the vacuum of space itself, and then re-emitted. This eerie event from the Boötes void forces a profound consideration. It suggests that the universe might, under conditions we do not yet understand, possess the ability to record and replay its own history. The empty void was not so empty after all, but a canvas for distortions in the very fabric of time. This temporal echo from the Boötes void was not an isolated incident. A similar, deeply unsettling mystery was unfolding much closer to home, tied to humanity's own silent ambassadors sailing through the void. The Pioneer 10 and 11 spacecraft, each carrying a golden plaque etched with a message for any beings that might find them, were the subjects of a different kind of anomaly. For decades, their positions were tracked with immense precision by teams of orbital dynamicists. Their predicted paths through the solar system were mapped with absolute certainty, governed by the steady, predictable pull of the sun's gravity. Then, a routine review of the old telemetry data revealed something impossible. On several distinct occasions, the data streams from the probes indicated they were suddenly thousands of kilometers off their calculated courses. It was as if, for a few brief hours, the spacecraft had simply jumped to a different location in space. The strangest part was what happened next. Just as suddenly, the telemetry would snap back, showing the Pioneers exactly where they were supposed to be, as if the jump had never occurred. The immediate assumption was a data glitch. Perhaps a burst of cosmic radiation had corrupted the signal. or a ground-based computer had momentarily malfunctioned. Yet a painstaking, in-depth review systematically ruled out every conventional explanation. It was not the push of solar radiation pressure. It was not a gravitational tug from an unknown asteroid. Nothing in the known physics of the solar system could account for such a sharp, temporary displacement. This left scientists with a profoundly weird possibility. What if the probes themselves had not moved through space, but had moved through time differently? The theory proposed that the spacecraft might have briefly drifted through a localized wrinkle in spacetime, a region where the flow of time itself was distorted. In such a place, the very fabric of causality could be temporarily suspended. For those few hours, the probe's clocks might have ticked at a different rate relative to Earth, making their reported positions seem impossibly wrong before everything resynchronized. This was not light bending away from mass or a signal echoing from the past. This was a direct suggestion that time, the most reliable constant in our daily lives, could develop soft spots, areas where its rigid forward march could stutter and skip. These anomalies with the pioneer plaques were a crucial piece of the puzzle, demonstrating that the universe's strangeness was not confined to distant quasars or cosmic voids. It was a fundamental property of reality, waiting to be triggered, and it was building toward the day when light itself would bend backwards. That specific date remains classified, but the event itself is catalogued in secure astrophysical databases as Temporal Anomaly 0. It began not with a single observatory, but with a cascade of simultaneous alerts that lit up monitoring stations across the globe and in orbit. Instruments designed to track gamma-ray bursts, to map the faint whisper of the cosmic microwave background, all registered a massive, coordinated spike of energy. It was not an explosion, but a distortion. The data pouring in from these independent sources painted the same impossible picture. From a region of space near the familiar glow of the Orion Nebula, photons were being observed behaving in a way that defied all logic. Their paths, as traced by ultra-sensitive detectors, seemed to loop and reverse mid-flight. It was as if light itself had hit an invisible wall and was forced to travel backwards along its own route. This was not the gentle bending of gravity around a massive star. This was a fundamental rewrite of light's most basic rule, its one-way journey through the cosmos. Renowned cosmologist Dr. Liam Chen, who later analyzed the consolidated data, described it with a chillingly precise term. He stated that the data suggests a temporary, localized inversion of spacetime geodesics. In simple terms, a geodesic is the straightest possible path through the curved fabric of the universe. It is the natural route any object, including light, will follow. For that path to invert, even for a moment, would be like the shortest road between two cities suddenly turning into a one-way street leading only back home. The question immediately became, what cosmic force could crumple the roadmap of reality itself? One compelling theory points to a transient wormhole. These are hypothetical tunnels through space-time, often visualized as a shortcut between two distant points. But what if this particular wormhole was unstable, its entrance and exit flickering? Light entering this turbulent gateway might not simply emerge elsewhere. It could be scrambled and spat back out the way it came, creating the observed backwards trajectory. Another, even more profound possibility involves quantum gravity, the long-sought theory to unify the large-scale world of relativity with the tiny, probabilistic world of quantum mechanics. In such a framework, the smooth geometry of spacetime might, at the very smallest scales, be a seething foam of bubbles that constantly form and disappear. The event near Orion could have been a moment when this quantum foam bubbled up into our macroscopic reality, creating a temporary pocket where the rules of cause and effect were suspended. A third, and perhaps the most mind-bending idea, is that we witnessed a brief interaction with a higher dimension. Imagine a two-dimensional drawing on a flat piece of paper. The line representing a beam of light can only travel forward or backward along that flat surface. But if you, a three-dimensional being, were to lift a section of that paper and fold it, the line could be made to touch a point behind its starting position. From the perspective of the two-dimensional world, the light would have just reversed its course. In our three-dimensional space, a similar fold through a fourth spatial dimension could produce the exact same effect. This singular event, the day light bent backwards, stands as the most direct and unambiguous challenge to our physical models. It forces a humbling realization. The very tools we use to see the universe, our telescopes and our theories, are built upon a set of assumptions that this anomaly simply brushed aside. It suggests that our understanding of reality is not just incomplete, but that there are entire chapters of physics waiting to be written. Chapters that describe a universe far stranger and more malleable than we ever dreamed. When faced with the impossible, a scientist's first instinct is to distrust the tools. Could the entire event have been a catastrophic failure of our own technology? A grand-scale illusion projected by faulty hardware? To answer this, a dedicated Tiger team of the world's top engineers and astrophysicists was assembled. Their mission was singular: to tear the data apart. They worked for months, combing through every line of software code that processed the signals, searching for a hidden bug that could invert a result. They examined every calibration log for the telescopes, checking for minuscule drifts in alignment or sensitivity. They ran diagnostics on every piece of hardware, from the massive radio dishes to the delicate optical sensors in orbit, looking for a malfunction that could cascade into a false reading. They investigated every conceivable external trigger, from powerful solar flares that could wash out detectors with electromagnetic noise, to cosmic rays striking a sensor and creating a phantom signal, and even the remote possibility of a sophisticated cyber attack designed to spoof the data. The investigation was exhaustive and the result was definitive. No single point of failure could be found. The most compelling evidence, however, came from the sheer diversity of the witnesses. This was not one telescope seeing something strange. Optical telescopes saw the starlight distortion. Radio telescopes charted the anomalous paths of long-wavelength photons. Even nascent gravitational wave observatories, which sense the ripples in spacetime itself, registered a corresponding tremor from the same region of space. These instruments work on completely different physical principles, for all of them to simultaneously malfunction and report the same impossible event, and for that malfunction to perfectly mimic a coordinated physical phenomenon, stretches coincidence beyond any reasonable limit. A simple error is therefore staggeringly improbable. With the integrity of the data confirmed, we are left with a far more profound conclusion. The universe itself, for one brief and inexplicable moment, truly did bend its own light backwards. This undeniable reality forces us to confront the ultimate question: what kind of cosmic architecture could possibly permit such a thing? The geometry of our universe is far from the simple, flat plane we intuitively perceive. To grasp how light could ever reverse its course, we must venture into the true, warped architecture of spacetime, a dynamic fabric where gravity sculpts profound and unexpected shapes. This is the realm of non-Euclidean geometry, where parallel lines can meet, and the angles of a triangle do not always add up to 180 degrees. In regions of unimaginable density, like around a black hole, this curvature becomes so extreme that the very paths light must follow, known as null geodesics, can be twisted into closed loops. Think of a mighty river flowing toward a waterfall. The water represents the forward flow of time and space. Now, picture a whirlpool forming at the edge, where the current circles back on itself. In this analogy, light caught in the grip of an intense gravitational vortex could theoretically, orbit a central point forever, never escaping. It is not flying away, it is trapped in a cosmic eddy. This is the foundation for one of the most staggering theoretical explanations: closed time-like curves. These are not mere loops in space, but paths through spacetime that could theoretically allow an object to return to its own past. The mathematics, first explored by luminaries like Kurt Gödel and later refined by Kip Thorne, show that under specific, exotic conditions, the fabric of reality could stitch itself into a knot where cause and effect are no longer a straight line. This leads directly to the concept of a traversable wormhole, a hypothetical tunnel through the substrate of the cosmos. While most wormhole models are unstable, collapsing instantly, a theoretically advanced civilization or a freak natural occurrence might stabilize one. If the entrance and exit of such a wormhole were to move relative to each other, or if its internal geometry were to flutter, light entering one end might not simply exit elsewhere. It could be thrown back along its own world line, creating the precise illusion of backwards travel we observed. This theoretical framework does not just explain a single anomaly, it redefines the possible. It suggests that the cosmic architecture includes structures so bizarre that they can fold time itself, turning the universe into a labyrinth where the past is not always a distant country, but a place you might accidentally stumble into. The cosmic web is not spun from the stars and galaxies we see. It is woven from something far more mysterious: the invisible threads of dark matter and dark energy that together make up over 95% of everything that exists. These are the prime suspects in our cosmic mystery, the unseen architects whose unknown properties could be warping reality itself. Picture the universe as a vast, invisible scaffold. Dark matter forms the massive filaments of this structure, its gravitational pull guiding the formation of galaxies and holding clusters together. But what if, in certain dense concentrations, this dark matter could do more than just pull? Theoretical simulations suggest that if certain hypothetical dark matter particles, like actions, interact in just the right way, they could theoretically twist the fabric of spacetime into temporary, unstable knots. Within such a knot, the paths that light is forced to follow could become so convoluted that they mimic a reversal, creating the illusion that light has bent backwards on itself. This is not a flaw in our instruments, but a feature of a cosmos built from materials we are only beginning to guess at. Meanwhile, dark energy presents an even more profound possibility. We know this force is causing the overall expansion of the universe to accelerate. But what if its density is not perfectly uniform? What if there are pockets of space where dark energy fluctuates, briefly intensifying or weakening? In a region where dark energy's repulsive force suddenly spiked, space itself would stretch at an accelerated rate. A beam of light traveling through such a turbulent zone could have its path radically altered, not by gravity, but by the very ground of reality rushing out from under it. One researcher working on these simulations noted that the required conditions are extreme, but not impossible within certain exotic models. This line of inquiry forces a humbling expansion of the mystery. We are no longer just questioning the behavior of the 5% of the universe we understand. We are staring into the abyss of the 95% that remains a complete enigma. If the fundamental forces we rely on are just a minor part of the story, then what other rules can be broken? What other impossibilities are waiting in the dark, and could some of them be the work of a mind, not just mindless physics? Perhaps these cosmic anomalies are not natural at all, but the residual signature of an intelligence operating on a godlike scale. When the laws of physics appear to be broken, one of the most profound possibilities we must confront is that someone or something has simply learned how to rewrite them. This is the extraterrestrial intelligence hypothesis, and it asks us to consider a civilization not just a few hundred years ahead of us, but millions. For such a culture, The manipulation of spacetime might not be a theoretical puzzle, but a foundational technology, as integrated into their society as electricity is in ours. We would not be looking for a deliberate message, but for an inadvertent clue, what scientists call a techno-signature. Imagine the hum of a massive power plant. The energy it radiates is not a broadcast, but it is unmistakable evidence of technology. In the same way, the daylight bent backwards could be the cosmic equivalent of engine noise, a side effect of a propulsion system that warps space to achieve travel, or perhaps the temporary activation of a communications network that uses folded spacetime as its medium. The sheer energy required for such a feat is beyond our comprehension, suggesting a mastery over the cosmos that borders on the magical. Leading astrobiologists urge caution, noting that nature is endlessly inventive and that extraordinary claims require extraordinary evidence. Yet they also concede that these specific events, with their precise, localized, and law-defying characteristics, do fit a hypothetical profile for a techno-signature. They represent a manipulation of the universe's most fundamental fabric, an effect that seems to require intent, or at least a level of control that mirrors it. This perspective fundamentally shifts the search for other minds in the cosmos. We are no longer just listening for a whisper in the radio static. We are scanning the heavens for the architectural scars of cosmic engineers. It forces a question that echoes back through our own history. If such beings exist and have been capable of these feats, might they have visited before? Could the faint, unexplained echoes in our own planetary record be the very clues we have overlooked, waiting to be understood not as myth, but as memory? These ancient chronicles are not merely stories. They are potential eyewitness accounts from a time before telescopes. A 12th-century monastic scribe in England recorded a night of profound terror, writing of a sky where the fixed stars themselves seemed to swirl in a great, backward-flowing river. On the other side of the world, Aboriginal Dreamtime stories passed down for generations speak of a time when the celestial river of the Milky Way shuddered and changed its course across the heavens. These descriptions, separated by vast oceans and entirely different cultures, share a chilling commonality. They describe the night sky not as a static tapestry, but as a fluid, dynamic entity that behaved in a way that defied all normal experience. When we strip away the mythological language, what are we left with? A swirling, backward motion of starlight, a sudden, perceived shift in the path of a galactic arm. To a modern astrophysicist, these are not just poetic turns of phrase. They are startlingly accurate descriptions of what a severe, localized distortion of spacetime might look like to the naked eye. A massive gravitational lensing event so powerful it could make the cosmos appear to writhe and flow in reverse. The sheer persistence of these specific themes across unconnected human societies is difficult to dismiss as pure coincidence. It suggests a profound possibility that the anomalies we are only now detecting with our most advanced technology have occurred before throughout human history. Our ancestors looked up and saw the laws of their universe temporarily suspended, and they recorded what they saw with the only vocabulary they had, the language of gods and omens. This historical thread weaves our own deep past directly into the modern mystery, transforming it from a distant astrophysical puzzle into a recurring feature of our cosmic environment. If these distortions have brushed against human perception for millennia, then the next logical step is to ask how such a thing is even possible on the most fundamental level. To find those answers, we must shrink our perspective from the vastness of the galaxy down to the ghostly, uncertain realm of the quantum. The bizarre rules that govern the tiniest particles in existence refuse to play by the same comfortable logic as our everyday world. Down in the quantum realm, particles can be in two places at once, a state known as superposition. They can tunnel through impenetrable barriers and remain spookily connected across light years through entanglement. These are not just quirks. They are the fundamental operating system of reality at its smallest scale. But what if these quantum effects are not confined to the microscopic? What if, under the right conditions, they can bubble up and manifest on a cosmic scale? This is one of the most radical explanations for the day light bent backwards. Imagine a vast region of space near the Orion Nebula not as a fixed, determined volume, but as a system in a quantum superposition of states. In one possible state, light travels forward as it always does. In another, equally real but far less probable state, the very geometry of that space allows light to travel backward. For a brief, unstable moment, that second state could have become real, a momentary flicker in the cosmic probability field. This would not be a mechanical bending, but a fundamental redefinition of the local laws of physics. Theoretical physicist Lee Smolin has proposed models where the universe's laws are not eternally fixed, but can evolve and fluctuate. In such a cosmos, the constants we hold sacred, like the speed of light, might only be averages. Rare quantum fluctuations could allow for temporary pockets where those constants change, or where causality itself becomes a suggestion rather than a rule. This perspective bridges the immense gap between the predictable clockwork of planets and the probabilistic weirdness of the atom. It suggests a universe that is not just strange in its distant corners, but fundamentally fluid and uncertain at its core. This profound shift in understanding forces us to ask a practical question. If the fabric of reality can flicker, how do we build an instrument to catch it in the act? The hunt for the next great cosmic anomaly has shifted from patient waiting to active pursuit, deep within the control rooms of facilities like the Vera C. Rubin Observatory. The atmosphere is one of quiet, automated vigilance. Banks of servers hum, not just processing images of the night sky, but actively interrogating them. The new paradigm is anomaly hunting, a systematic search for the statistical ghosts, the one data point in a trillion that does not belong. This is no longer about human eyes scanning endless star fields. It is about machine learning algorithms, trained on vast simulations of every conceivable strange event. These digital sentinels are taught to recognize the subtle fingerprints of impossible phenomena. They do not just look for a flash of light, but for a cascade of correlated impossibilities. They might flag a distant quasar whose light shows a specific, unnatural redshift at the exact same moment. A gravitational wave observatory detects a tremor from the same patch of sky. This multi-messenger approach is key, layering data from light, gravity, and even ghostly subatomic particles to build an unassailable case for the truly weird. The next frontier involves neutrino detectors, sensing nearly massless particles that travel straight through matter, and future space-based observatories like LISA, which will listen for the low-frequency ripples of spacetime stirred by colossal events. By weaving these signals together into a single cosmic net, scientists are transforming the search from a game of chance into a rigorous experiment. The goal is not just to catch the next event, but to capture it with such rich, multi-layered detail that its nature can no longer be denied or dismissed. This proactive stance raises a tantalizing prospect. If we can understand the precursor signals, the faint whispers in the data before the storm, could we one day not just observe these cosmic lawbreakers, but actually predict their arrival? The universe is not a simple, solid sphere, but something far more intricate and pliable. To truly grasp how light could reverse its own path, we must explore the most extreme blueprints that physics can draft, structures like wormholes and white holes. Think of the cosmos as an apple. An ant walking on its surface must travel the long, curved arc from one side to the other. But if a worm burrows straight through the fruit's core, it creates a shortcut, a tunnel connecting two distant points on the skin. A wormhole is this concept scaled up to a cosmic level, a hypothetical bridge through the substrate of spacetime itself. A stable, traversable version of such a tunnel could theoretically allow a beam of light to enter, and due to the complex internal geometry, exit in a way that makes it seem from our external perspective as if it has traveled backwards. The mathematics of general relativity not only allows for this, it demands it as a possibility. Yet there is a catch. Keeping this tunnel from instantly collapsing requires a form of matter with truly bizarre properties, something known as exotic matter. This is not antimatter. It is a theoretical substance that possesses negative energy density, effectively propping the wormhole's throat open against the crushing force of gravity. Then there is the even more enigmatic white hole. If a black hole is a cosmic drain from which nothing, not even light, can escape, then a white hole is its theoretical opposite, a gushing fountain. It would be a region of spacetime where matter and energy can only pour out, a violation of the one-way street we observe everywhere else. A sudden, localized eruption from a white hole could appear as a brilliant, law-defying event, spewing light in a manner that completely inverts our understanding of cause and effect. While no white hole has ever been observed, its existence is a perfectly valid solution to Einstein's field equations. These concepts are far more than just science fiction. They serve as a crucial mathematical playground, allowing physicists to stress-test the rules of reality to their absolute breaking point. They hint that the universe might be threaded with such fantastical structures, hidden from view but capable of producing the very impossibilities we are now struggling to explain. Our universe might not be the only one. The strangest events ever recorded could be the first tangible evidence that we are not alone in the grand scheme of existence, but surrounded by an infinite sea of other realities. This is the multiverse hypothesis, a concept that emerges naturally from the leading edges of quantum mechanics and cosmic inflation theory. Picture our entire cosmos not as the entirety of everything, but as a single bubble in a vast, frothing cosmic foam. Each of the other bubbles in this foam is its own separate universe, potentially with its own unique and alien set of physical laws. In one universe, gravity might be repulsive. In another, the speed of light could be a slow crawl. The constants we consider fundamental might be nothing more than local bylaws. The radical idea is that these bubbles can sometimes brush against each other. The daylight bent backwards could have been a moment when our universe developed a temporary bruise, a thin spot where the barrier between our reality and another grew weak. For a fleeting instant, the laws from that neighboring universe bled into our own. In a reality where light naturally travels in loops or even backwards, its brief influence over our local spacetime would produce the exact impossible phenomenon we observe. It would not be a malfunction of our cosmos, but a momentary infection by a foreign physics. This is not just wild speculation. Cosmologists like Max Tegmark have systematically categorized how such parallel realities could exist, from the simple level of regions beyond our cosmic horizon to the profoundly strange levels where entirely different mathematical structures govern existence. While we have no direct proof, the idea reframes every anomaly not as a breakdown, but as a glimpse. The echo from the void and the jumping probes might be echoes of these collisions, moments when the fabric of our solitary bubble trembled from a contact we cannot yet fully perceive. This possibility challenges the bedrock of what we call reality, suggesting that the most fundamental rules of existence are not universal, but merely provincial. A single press conference could shatter our worldview forever. Imagine a stage, bright with camera lights, where a spokesperson from a leading global scientific body steps to the podium. Their statement is simple and unequivocal. The anomalies have been analyzed, and the data points to a single, staggering conclusion: an intelligence beyond Earth is responsible. The air seems to leave the room. In that moment, the quiet, mechanistic universe we thought we understood vanishes, replaced by a cosmos that is not only stranger than we suppose, but stranger than we can suppose. This is not a distant scientific curiosity. It is a direct challenge to the very foundations of human thought. For centuries, our religions, philosophies, and cultures have been built upon the assumption of human centrality. We are the storytellers, the explorers, the soul-bearers of consciousness gazing out at a silent, inanimate void. That narrative would collapse overnight. How would our drive for exploration transform? The old dream of planting a flag on a distant world would feel quaint, replaced by a humbling quest for understanding. Would such a revelation unite humanity, presenting us with a common, cosmic neighbor, or would it fracture us further, creating new hierarchies between those with access to the truth and those left in fear? Our ethical systems would face their greatest test. How do we define rights, value, or personhood when the other is utterly alien? The discovery would force a profound re-evaluation of our place in the cosmos. We would no longer be the protagonists of the universal story, but perhaps merely a single sentence in a sprawling, galactic epic. This shift from a lonely outpost to a resident in a teeming metropolis of mind is the ultimate paradigm shift. It invites a deeply personal reflection. Where does your own life, your struggles and your joys, fit into a universe that contains engineers of space-time? The thought is dizzying, a simultaneous shrinking of our individual significance and an immense expansion of our collective potential. This is no longer a question of if we are alone, but a preparation for when we finally realize we never were. The silence of the cosmos has always been its most deafening feature. For decades, the Fermi paradox has haunted our search for other life, posing a simple, devastating question. If the universe is so vast and so old, where is everybody? The strange events we have been investigating offer a chillingly elegant answer. They are not missing. We have simply been looking for them in the wrong way. Like an ant on a circuit board searching for a handshake, while the entire computer hums with purposeful activity around it. Our search has been focused on finding deliberate messages, a cosmic hello in a language we understand. But what if a civilization a million years more advanced than us does not communicate with simple radio waves? What if its technology is so deeply integrated with the fabric of reality that its everyday operations are the anomalies? The daylight bent backwards may not be an unsolved mystery of physics. It could be the equivalent of spotting the wake of a ship on a distant ocean. We are not seeing a natural storm. We are observing the passage of an engine so vast it warps the very sea of space it travels through. This reframes the entire paradox. A Type 3 civilization on the Kardashev scale, one that harnesses the power of its entire galaxy, would not need to send us a message. Its activities would be galactic in scale, and their signatures would be written in the distortion of spacetime itself. We have been sifting the cosmic static for a whisper, while all around us the background noise of the cosmos crackles with the evidence of engineering. Detecting this requires a fundamental shift in science, moving from simply observing the universe to forensically analyzing it for signs of design. We must learn to distinguish between a natural earthquake and the tremor of a machine so large it uses stars for gears. The great silence is not empty. It is filled with a technology we are only just learning how to see. That piercing signal from the void arrived on a quiet August night in 1977. The Big Ear radio telescope in Ohio was engaged in its routine sky survey when a pen chart recorder traced out a spike of such intensity and purity that the astronomer who found the data printout, Jerry Amon, simply circled the alphanumeric code and wrote "Wow." In the margin, the signal was strong, it was narrowband, meaning it was focused on one specific frequency, and it lasted for 72 seconds before vanishing forever. It perfectly matched the expected signature of an artificial transmission from deep space. For decades, the Wow signal has been the holy grail of potential alien contact, a single, tantalizing shout in the dark. But what if we have been misinterpreting its nature entirely? It was not a deliberate hello, but something far more mundane for its sender, a brief, unavoidable leak of energy. Consider the immense power required to manipulate space-time on a cosmic scale. The process of bending light or stabilizing a wormhole would demand energy outputs dwarfing entire stars. A momentary fluctuation in such a system, a power surge in a cosmic engine, could easily produce a brief, powerful, and narrowband radio burst as a side effect. The Wow signal's characteristics align not with a crafted message, but with the theoretical exhaust of a technology operating on principles we can barely conceive. It was not a sentence, it was the hum of a motor. This same logic applies to the enigma of fast radio bursts. These are not gentle whispers, but violent, millisecond-long blasts of radio waves that travel billions of light-years across the universe. They pack more energy than our sun emits in 80 years, and then they are gone, sometimes repeating from the same source in unpredictable patterns. Their origins have been one of astronomy's greatest puzzles, with explanations ranging from colliding neutron stars to evaporating black holes. Yet, when viewed through the lens of cosmic engineering, a more profound possibility emerges. The sheer, focused energy of an FRB is precisely what you would expect from a controlled, catastrophic release of power. Imagine the ignition of a space-time drive, a single, calibrated pulse to open a temporary gateway or correct the trajectory of a massive object. The resulting shockwave through the interstellar medium would manifest as one of these brilliant, fleeting bursts. Some FRBs even show a strange Faraday rotation effect, suggesting their light has twisted through an immensely powerful magnetic field, the kind that could be generated by an artificial structure of staggering size. They are not natural cosmic explosions. They are the brief, brilliant flashes from a celestial construction site, the signature of a universe being actively shaped by forces that have mastered its fundamental rules. Connecting the solitary Wow signal to the scattered, powerful FRBs creates a cohesive, if unsettling, picture. We are not listening for a conversation. We are witnessing the background industrial activity of a cosmos buzzing with intelligence, its presence revealed not by its words, but by the unavoidable radiation of its incomprehensible works. This pattern forces the next logical and deeply personal question. If the universe is this active, how close has this cosmic activity come to our own world? At the heart of every galaxy lies a gravitational monster, a black hole whose pull is so absolute that not even light can escape its grasp. These cosmic paradoxes, where our understanding of physics breaks down, could be the very engines driving the anomalies we have witnessed. To understand how, we must take a theoretical journey to the precipice of a supermassive black hole. Just outside its event horizon, the point of no return, the fabric of space-time is not just curved. It is being violently whipped into a frenzy by the black hole's immense spin. This phenomenon, known as frame dragging, means that space itself is being dragged around the rotating black hole like a whirlpool dragging water along with it. In this region of extreme physics, the paths that light must follow, its geodesics, can be twisted into such tight knots that they form closed loops. A photon could, in theory, orbit the black hole countless times before either falling in or being flung back out. From a distant observer's perspective, this could create the perfect illusion of light bending backwards on its own trajectory, trapped in a relativistic vortex. This is not a violation of the laws of physics, but their most extreme and unfamiliar consequence. The strangeness only deepens when we consider what happens to information that falls into a black hole. According to quantum mechanics, information can never be truly destroyed. Yet, according to general relativity, anything crossing the event horizon is lost forever. This is the famous black hole information paradox. To resolve it, physicists like Leonard Susskind proposed the holographic principle, a staggering idea that all the information about what falls into a black hole is not lost inside, but is instead encoded on its two-dimensional surface, the event horizon, like a cosmic hologram. The three-dimensional reality we perceive is, in a sense, a projection from this encoded data. Now, consider the implications. If a black hole is constantly processing and encoding information on its boundary, could the bizarre phenomena we detect, the temporal echoes, the backwards light, be a rare macroscopic leakage of this quantum information processing? Could we be witnessing the universe's own data storage and retrieval system in action? A glitch in the cosmic matrix where information is briefly projected back out into space. Suskind's later work on firewalls and complementarity further complicates the picture, suggesting that our simple, classical view of a placid event horizon is profoundly wrong. The boundary of a black hole may be a seething, energetic region where quantum gravity reigns, a natural laboratory for physics we have yet to discover. These objects are not just passive drains. They are dynamic, complex entities that might actively warp reality in ways we are only beginning to glimpse. The fundamental forces that hold our universe together are balanced on a knife's edge. The strength of gravity, the power of the nuclear forces, the mass of an electron, these are not arbitrary numbers. They are the universe's foundational settings. If the force of gravity were even a fraction of a percent stronger, the cosmos would have collapsed back in on itself moments after the Big Bang. If it were slightly weaker, no stars or galaxies would have ever clumped together from the primordial gas. The same razor-thin precision applies to every other constant. This is not a matter of chance, it feels like a setup. The anthropic principle steps into this eerie fine-tuning with a simple, yet staggering, proposition. It states that we can only observe a universe that has the specific properties necessary for our existence. We are here because the numbers allow us to be here. This logic, however, does not just apply to the existence of stars and planets, but to the very nature of reality we are able to perceive. A universe stable enough to produce conscious life is necessarily a universe of immense complexity, with layers of physics built upon physics. And within that deep complexity, profound mysteries are not just possible, they are inevitable. The anomalies we have chased, the backwards light and the temporal echoes, might not be glitches in the cosmic code. They could be features of a system so rich and intricate that its full operating manual is beyond our current comprehension. We are like ants who have just discovered the transistor, baffled by a technology that is part of a larger, functional whole we cannot yet see. This perspective transforms our quest from solving errors to exploring frontiers. The universe's strangeness is not a problem to be fixed, but a wilderness to be mapped. It asks a deeply reflective question: is our drive to investigate these cosmic paradoxes not just a scientific pursuit, but an intrinsic part of our purpose as conscious observers? Perhaps we are not just accidental inhabitants of a clockwork universe, but the universe's own way of beginning to understand its deepest, most beautiful, and most bewildering secrets. This quiet revolution in our approach is already taking physical form on engineering drafting tables and in mission simulation labs. The next generation of explorers will not be telescopes staring from a distance, but dedicated probes sent on daring voyages into the unknown. These spacecraft, with working titles like the Anomaly Mapper, are being designed for one purpose only: to actively interrogate the sites of our greatest cosmic mysteries. Imagine a vessel unlike any other, its hull studded not just with cameras, but with a suite of hyper-specialized sensors. Some are designed to measure the minute stretching and compressing of spacetime itself, listening for the faintest gravitational tremors. Others are calibrated to detect the faint shimmer of quantum field fluctuations, the ghostly activity of virtual particles popping in and out of existence. The most ambitious instruments would even attempt to measure non-local correlations, looking for the subtle, spooky connections that might bind distant points in space. The mission profile is as bold as the technology. Instead of observing from the safety of Earth's orbit, these probes would be dispatched directly to the last known coordinates of past anomalies. They would travel to the silent patch of sky near Orion where light once reversed its path, or venture toward the echoing emptiness of the Boötes void. Their trajectory would be a calculated gamble, guided by new cosmological models that predict statistical hotspots for reality-bending events, places where the fabric of the cosmos might be inherently thin or unstable. Upon arrival, the real work begins. These robotic investigators would release calibrated pings of energy across the spectrum, from laser light to gravitational waves, watching intently for any distortion in their return. They would deploy sensitive magnetometers to hunt for the impossible signature of exotic matter, the theoretical substance with negative energy that could keep a wormhole's throat propped open. They would map the local geometry of space with microscopic precision, searching for any residual scarring, any permanent warp or twist left behind from a previous violation of the laws of physics. This represents a fundamental shift in human exploration. For centuries, we have been cartographers of the cosmos, patiently mapping the stars and galaxies we can see. Now, we are becoming its diagnosticians. We are moving from simply observing the symptoms of a strange universe to actively taking its pulse, probing its wounds, and attempting to understand the underlying illness. We are no longer satisfied with watching the ghost from the doorway. We are stepping into the room with our instruments at the ready, determined to learn its name. The silence we maintain might be our greatest shield or our most tragic failure. As we stand on the verge of potentially detecting a clear, undeniable techno-signature, a profound ethical dilemma emerges. Do we send a greeting into the void, or do we remain silent observers? This is not a question for astronomers alone, but for all of humanity. The precautionary principle, long used in environmental science to advocate for caution in the face of uncertainty, must now be applied on a cosmic scale. Our most powerful investigative tools are not passive. Aiming a concentrated laser signal or a focused radio burst at the source of an anomaly is not like turning a camera lens. It is an active pulse of energy, a deliberate tap on a shoulder in a dark room. To a civilization capable of bending space-time, such an act might be interpreted as anything from a friendly hello to a territorial challenge. We have no way of predicting the psychology or the protocols of a mind that could use stars for fuel. The potential reward is a transformative leap in knowledge, an understanding of physics that could solve our energy crises, unravel the nature of consciousness, and grant us the stars. But the risk is the complete unknown. Our entire history is a chronicle of what happens when technologically unequal cultures meet, and the results are rarely good for the less advanced one. Yet the risk of inaction is equally staggering. To turn away from the possibility of contact, to willfully ignore a beacon in the dark, would be to deny a fundamental part of our nature as explorers. It would be to choose a safe, sterile ignorance over a dangerous, vibrant truth. This forces a conversation we are not having, a global, multidisciplinary dialogue that must include philosophers, anthropologists, historians, and diplomats alongside our physicists and engineers. How does humanity, with all its divisions, present itself on the cosmic stage? Do we speak with one voice, and if so, what does that voice say? The answers will define our species for millennia, determining whether we become wise participants in a cosmic community or remain forever silent, afraid of the echoes we might hear. The greatest cosmic mysteries cannot be solved by a handful of scientists in isolated labs. They demand a global network of eyes and minds, a collective effort that is now being unlocked through the power of public engagement. Imagine a digital platform, open to anyone with an internet connection, where you can access the same raw data streams from the world's most powerful telescopes. This is not a futuristic dream, It is the emerging reality of citizen science. Amateur astronomers and data enthusiasts are now logging in to sift through terabytes of cleaned, public data, running their own custom algorithms to hunt for the statistical ghosts that professional teams might miss. The model was pioneered by projects like SETI at home, which used distributed computing to analyze radio signals, but the new frontier is far more interactive and intuitive. Volunteers are not just lending their computers processing power, they are lending their own pattern recognition skills. They are classifying the bizarre, flickering light curves of distant stars that might indicate a megastructure, or identifying the subtle, warped signatures of gravitational lenses that do not match any known model. They are monitoring real-time feeds from orbital observatories, serving as the first line of defense against the next great anomaly. This distributed intelligence is a formidable force. Where one professional might see noise, 1,000 amateurs working in concert can identify a signal through the sheer weight of collective scrutiny. This process does more than just accelerate research. It fundamentally demystifies the scientific endeavor. It transforms abstract cosmic mysteries into a tangible, collaborative human adventure. When you are the one who flags a star that behaves strangely, you are no longer just a passive observer of the cosmos. You become an active participant, a cosmic detective with a stake in the outcome. This fosters a profound sense of shared cosmic citizenship, a realization that the quest to understand the universe belongs to all of us. By empowering everyone to look, we exponentially increase our chances of seeing, turning the greatest puzzle of all into a shared human journey. A recent viral story claimed a distant star had dramatically winked out of existence, sparking fervent speculation about a constructed Dyson sphere blocking its light. The truth, once uncovered, was far less sensational but no less fascinating. A thick, localized cloud of interstellar dust and rock had simply drifted in front of the star, dimming its output in a perfectly natural, if rare, celestial transit. This is the critical juncture where genuine cosmic mystery parts ways with popular hoax. The Internet's echo chamber often amplifies the spectacular while ignoring the simple explanation. Applying a principle known as Occam's razor is our most vital tool here. This idea suggests that the simplest explanation, the one requiring the fewest new assumptions, is most often the correct one. Before leaping to a conclusion involving alien engineers, we must first exhaust all possibilities involving known physics and natural phenomena. Consider the countless videos online purporting to show unidentified flying objects performing impossible maneuvers. A significant portion of these can be traced back to more mundane sources. High-altitude weather balloons caught in unusual light can appear to dart and shift. The predictable, bright train of Starlink satellites seen shortly after launch is routinely mistaken for a fleet of otherworldly craft. Even more common are camera artifacts. A lens flare from a bright planet, internal reflections within the complex glass of a telephoto lens, or simple digital compression glitches can all create convincing illusions of structured objects in the sky. These are not lies, but misunderstandings of the technology we use to see the world. This is why the scientific process remains our anchor in a sea of speculation. Real discovery is slow, meticulous, and collaborative. A single, strange photograph is merely a curiosity. For an observation to become evidence, it must be reproducible. Other teams, using different equipment, must be able to observe the same phenomenon under the same conditions. Then comes the gauntlet of peer review, where experts in the field scrutinize every step of the analysis, searching for flaws in methodology or interpretation. This system is deliberately slow and skeptical, designed to withstand the hype cycle and isolate genuine breakthroughs from the noise of error and hoax. This rigorous mindset is not a killjoy that strips the universe of its wonder. On the contrary, It is the very filter that allows true wonder to shine through. When we can confidently rule out the satellite, the lens flare, and the dust cloud, what remains is the genuinely inexplicable. The backwards light, the temporal echo, these events have passed through this very filter. They persist not as fuzzy videos on social media, but as hard, repeatable data points that challenge our fundamental models. By equipping ourselves with this critical thinking toolkit, we ensure our search for the cosmos's deepest secrets remains focused on the signal, and not the endless, distracting static. So many disparate clues from across the cosmos point toward a single, unsettling possibility. Let's pin them all to a vast cosmic board, connecting them with red string. Here is the Boötes Void Echo, a perfect recording from the past. Over here, the Pioneer probes that seem to jump through time, and at the center, the daylight itself bent backwards. The question is no longer what each event was, but whether they are all connected. Are they isolated glitches, or are they different symptoms of the same underlying cosmic condition? The search for a pattern begins with timing. Did these anomalies occur randomly over decades, or do their dates align with our solar system's slow, 250 million year orbit around the galactic center? Perhaps they cluster when we pass through one of the invisible rivers of dark matter that web the galaxy, their exotic gravitational influence temporarily warping local reality. The locations offer another clue. Are these events scattered randomly, or do they map onto specific, geometrically strange regions of spacetime, places where the cosmic fabric is inherently thin or warped? One compelling synthesis proposes that we are witnessing different faces of the same phenomenon, a spacetime storm. Just as a terrestrial hurricane involves low pressure, high winds, and torrential rain all at once, a cosmic storm might manifest as a gravity reversal here, a temporal echo there, and a light inversion somewhere else, all driven by the same turbulent core. Another unifying idea points to a macroscopic quantum fluctuation. At the smallest scales, empty space is a seething foam of virtual particles. What if, on rare occasions, this quantum frenzy doesn't cancel itself out? What if it bubbles up into our reality, creating a temporary pocket where the rules are rewritten, explaining everything from the Pioneer's jump to the backwards light? While a single, elegant equation that ties it all together remains beyond our grasp, the very act of synthesis is a powerful compass. It tells us we are not chasing a dozen separate ghosts, but a single, multifaceted mystery. It forces our gaze away from the anomalies themselves and toward the empty spaces on the map between them, the silent voids and the calm stretches of space-time. For it is in the quiet that the next great pattern will likely emerge. Our journey through the cosmos's strangest events paints a new portrait of reality, one that is fluid, mysterious, and endlessly astonishing. We began in an era of scientific certainty, confident the universe was a predictable clockwork, only to be humbled by a single crack in that foundation. We witnessed the day light itself bent backwards, investigated echoes from an empty void, and tracked spacecraft that seemed to dance with time. We've weighed every possibility, from profound instrumental error to the existence of negative mass, from the tremors of a nascent quantum gravity to the staggering possibility of cosmic engineers. The ultimate conclusion is not a tidy answer, but a profound shift in perspective. These anomalies are not the death of our understanding, they are its rebirth. They are the vital fuel that pushes science forward, forcing us to ask bigger questions and draft new blueprints for reality. The universe is not a puzzle to be solved, but a frontier to be explored, a dynamic and living thing that still holds countless secrets. As Carl Sagan so perfectly expressed, somewhere, something incredible is waiting to be known. Let this investigation be your starting point. The next time you look up at the night sky, see it not as a static picture, but as a deep and shifting ocean of possibility. What do you think is the most compelling explanation for these cosmic mysteries? Share your thoughts in the comments, And if your curiosity is sparked, subscribe to continue this journey of discovery together.